Hello all, welcome back to my YouTube channel all about VLSI. In this video, we are going to continue the discussion of our AHB coding. In our previous video, we have started with AHB coding and we have seen the Verilog code for single incremental burst. Now in this video, we are going to discuss about how to implement INCR4 burst and INCR8 burst in Verilog. Let us continue our discussion. We are basically started our discussion on master code development, implemented a single incremental burst. Now let us try to implement a INCR4 burst. So this was our code, and in this what I am going to do is, first of all, in the ideal state. So if you haven't watched the previous video, I recommend you to once rewatch the previous session so that you can continue them. You can maintain the continuity. So in this ideal state, we have written the logic for our incremental burst, single incremental burst. So this was the logic for our single incremental burst. Now let us write down the logic for our INCR4 burst. Okay. Now, so I've already written this is for my single incremental burst. Now let's write the logic for our INCR4 burst. So within an else if right underscore top is equal to 1, that is if it is a write operation, and my h ready is equal to 1, and beat length if it is equal to 4, and my enable is equal to 1, and wrap underscore enable is equal to 0, then I'm going to a state which is nothing but wrap enable is equal to 0. Then I'm going to a state, next state is equal to next underscore state, which is equal to right underscore state underscore address. The same state I will be going to, and my h burst will be equal to 3-tick binary 011. So for my INCR4 burst, my h burst will be equal to 011, and my h write will be equal to 1, followed by n. So this was my code in the ideal state. This was my code in the ideal state for INCR4 burst. Okay. Now this is my right state address. In the previous video we have seen, right? This is my right state address, and in this state I have written the code for my INCR burst. Now let me write down the code for my INCR4 burst. Code for INCR4 burst. Let us see the code for our INCR4 burst in the right state address. Basically, we are going to else if my h burst is equal to 3-tick binary 011, and then we are simply making our h trans is equal to 2-tick binary 10. That means it is a non-sequential address. So the first data in the burst will be a non-sequential transfer, and simply I'm going to next state, which is known as write state data, which is nothing but our write state data, and within begin and block I'm going to write down. So previously also I was doing the same thing. Okay, here also the same thing. Okay, now I'm going to a state which is known as write state data. Let us see the logic for our write state data. So here I have already written the code for my INCR burst. Now let us write down the code for my INCR4 burst. So else if h burst is equal to 3-tick binary 011, begin this. So here what I am going to do is hw data, which is equal to mem of read underscore pointer. So what I am doing, I am assigning my hw data, which is equal to the data which is present inside my FIFO memory. Okay, using the read pointer I am accessing it. So initially your read pointer will be equal to 0, and initially your read pointer will be equal to 0. So by incrementing this read pointer sequentially, I'm accessing the data from this memory and I'm assigning it to my HW data, and it is a H burst is nothing but 011, that is it is an incremental 4 burst, INCR4 burst, right? So the 4 data items, the 4 data packets I'm sending it, and my H trans in this particular case, it will be equal to 2-tick binary 1 1. That means it is sequential in nature. And let me declare the read pointer, write underscore pointer, comma read underscore pointer. Now here I need to send 4 data items. So how to send this 4 data items? And so for that particular thing, I am going to consider a count logic. So I am going to have a count, and if the count has reached the 4 cycles, after 4 cycles of count, then I'm going to the next state, which is nothing but my idle state. So I should write down that particular logic, and I cannot use this count logic inside my next state logic block, because next state is a combinational logic. So I should declare my count logic inside my present state. So this is my combinational block. Next state logic is a combinational block. So in the present state, I should use my count logic. So how to write this count logic? Let us see. So if reset, we have seen this count is equal to 0, else present state is equal to next state. This we have already written. Now in this, we need to write down our count logic also. Let us see how to write this count logic. Now here I am going to write down my count logic. So if my present state, which is equal to write state data, if my present state is equal to write state data, and if my beat length is equal to 4 and my h ready is equal to 1, and wrap underscore enable is equal to 0, then what I'm going to do is, then what I am going to do in this particular thing is begin count is equal to count plus 1. So what I'm doing, basically I'm checking for my present state. If my present state is equal to write state data, and if my beat length is equal to 4, if my beat length is equal to 4 and my HRD should also be 1, and wrap enable is equal to 0, then I am then I am incrementing my count. Count is equal to count plus 1. I'm just simply incrementing my count, and also I'm incrementing my read pointer. Read underscore pointer is equal to read underscore pointer plus 1. Only whenever I am in my write state data and beat length is equal to 4. In these two cases only, I am incrementing my things. Okay. And followed by address also I will increment. Address underscore internal. This is my internal address, which is equal to address underscore internal plus tick h4. Why 4? Because your size of the data is 4 byte. Okay, so I'm incrementing my address by 4 byte. Okay, and this address underscore internal will be assigned to the h address. In the code we have seen it. Let me show you. Okay, so here we have assigned it. So in the hw data state only, so in the write state data only, we are incrementing this address, and it will be incremented by 4 bytes, and it is assigned to h address. Okay, so this is what I've written inside this uh, sequential block. Okay, so incrementing logic I've written inside the sequential block, that is a present state logic only I've written it, because it is a sequential block, you can see. Whereas I have not written this it in the next state logic. Incrementing logic is only written in the present state block, and followed by n I've written. Now coming back to the write state data, where we have seen, yes, this one. So else if hburst is equal to 011, hw data is equal to mem of read pointer, and htrans is equal to 2-tick binary 11. This we have written, and here we are going to check for the count variable. Here we are going to check for the count variable. If my count is equal to beat length minus 1, or you can simply write if your count is equal to 3. Okay, anything you can write. You can write if count is equal to beat length minus 1, or your count is equal to 3. That is 0, count is equal to 0, 1, 2, 3. That is 4 cycles. Okay, so if count has reached 4 cycles, then I will simply go to next state, which is nothing but idle. Next state is equal to idle. Else my next state, I am going to stay in the same state, that is write state data. Okay, so this is the logic which I have written for my next state. So here if my else if hburst is equal to 011, and this will come inside this one. So else if we are basically we are checking for my H burst whether it is 011. If it is 011, I'm assigning HW data. I'm accessing the data from the FIFO and I'm giving it to HW data, and read pointer is incremented for every cycle in the sequential logic, that is in my present state logic, and my H trans is equal to 1 1, that is it is a sequential transfer. And I'm also checking whether my count is equal to 3. Count variable is also incremented in your present state logic because it is a sequential block. For every cycle, it is going to be incremented. And since it is in a 4-bit burst, what we are going to do is we are basically waiting for count to become 4, count to become 3. That is, we are basically counting for 4 cycles. After counting 4 cycles, that is, after sending 4 bits of data, we are simply going to the idle state, or else we are going to stay in the same state, right state data. Okay, so this is the logic which we have written, and this is a simple logic which we have written. And yes, now let us try to write down our slave logic, and after writing the slave logic, we will write down the test bench and test our design. So this is my slave logic which I'm going to write down, which is going to have input as h clock and input h reset in, input h reset, and input 31 down to 0 address, and input h write, and input 2 down to 0 h size, and input 2 down to 0 h burst, and input 1 down to 0 h trans, and input 31 down to 0 hw data, and output reg h ready is our output to our slave. These are all the signals which are associated in the specification. Also, these are the signals which are declared in the specification. Output h response, and output reg 31 down to 0 hr data. So these are the inputs and outputs of our slave. Now let us declare some parameters. So parameter idle, which is equal to 2-tick binary 00, and parameter sample underscore state, which is equal to 2-tick binary 01, and parameter write underscore state 2-tick binary 10. Since we are checking for only write operation for now, we are going to focus more upon write only. Okay, so one more parameter I will declare. In future, we will discuss about read operation. Write underscore state underscore ready, which is equal to 2-tick binary 11. Okay, so these are my states which I have declared now. So I will declare reg 1 down to 0 present state comma next state. So let me write down the let me write down the present state logic. Always at passage of clock begin if reset underscore h reset. If h reset, then begin present state will be equal to idle. Else my present state will be equal to next state followed by end. So this is my present state logic. Now, so I have declared them as PS and NS, and this is H clock. Yes, so I've declared them. Next, let me write down my next state logic. So in the next state, what I'm going to write down is always at the rate star. It is a combination logic which we are going to write down. Begin. So always at the rate star begin. Case of my present state, which I'm going to write down. If I'm in my idle state, begin I'm just simply making my h ready is equal to 1. Slave, it's a simple logic which I'm writing down. And next state, I'm going to a state which is known as sample underscore state followed by n. And next in my sample underscore state, what I'm going to do is I'm going to assign my I'm going to sample my trans signal h trans underscore internal is equal to h trans. Let me declare this signal also h trans underscore internal reg 1 down to 0 h trans underscore internal for collecting my transfer signal, and I will also declare one signal h write underscore internal for collecting my h write signal, and reg address underscore internal reg 31 down to 0 address underscore internal for collecting my internal address into my internal address. Okay, so I will write down here. I'm basically sampling the data h write underscore internal which is equal to h write, and address underscore internal which is equal to h address. So I'm collecting them, I'm sampling them basically. After that followed by n, and yeah, so before that I should check for one condition. What is that condition is, if my h trans underscore internal is equal to 2 tick binary 10, that is it is a non-sequential transfer, or if my h trans underscore internal is equal to 2 tick binary 11, it is a sequential transfer. If it is a non-sequential transfer or it is a sequential transfer, then my next state, and also I'm checking for my h write. If my h write is equal to h write underscore internal is equal to 1, then basically I'm going to a next state which is known as ns is equal to write underscore state, or else I'm going to a state which is known as read underscore state. I haven't declared that state. In future I will declare. Okay, now so let me write down the logic for my write state. So in the write state, I'm basically writing my hr I'm basically writing my hr data is equal to hw data. I'm basically doing the loop back, and if my h trans underscore internal is equal to 2 tick binary 00, that is if it is an idle state, then my next state will be equal to idle only. That's it. And so this is my slave logic. So basically I'm checking for my, in the write state, basically I'm collecting the data from the HW data and I'm giving it to HR data directly. Okay, basically I'm looping back. Okay, whatever the data master is sending, I'm looping back, and I'm checking for my h trans underscore internal to become 00. That means master is in idle state. If master is in idle, then the slave will also go back to idle state. Okay, and during this entire process, my h ready is equal to 1. That is, my slave is already always ready. Okay, and followed by end case and end, followed by end module. So here I should write it as ns, and here it is ps. So this is the logic for my slave module. Now let us write down the logic for our test bench and let us verify our design. So I've declared my internal variables clock, reset, data top, write top, wrap enable, h ready, h response, hr data enable, address underscore top, h address, and h write, h size. I've declared them, and here I'm instantiating my master, and also I'm instantiating my slave. So this is my master and this is my slave which I'm instantiating. And after that I'm initializing my variables and generating my clock. After generating my clock, what I'm doing is first of all applying the reset signal, and after that removing the reset signal, and I'm checking for the FIFO full condition. If FIFO full is equal to 0, then I'm starting this write underscore top is equal to 1. That means it is a write operation. And After that, I'm giving the base address, that is 0000. All the base address is 0. And I'm giving the data, 4 data items I'm giving. And after that, I'm also specifying the beat length, and I'm making my enable is equal to 0. So this is what I have given. So let's see the waveform, what are we getting? So this is the waveform which I'm getting, and this is my clock and reset. So my head steady is equal to 1. It was made by the slave, and you can see the data top which we are giving from the test bench. First data is 1, next is some data 1 2 3 4, and 002 and 003. Okay, and my right underscore top is equal to 1 by the test bench, and my beat length is equal to 4. Okay, so beat length is equal to 4 they have given, and enable is made to 1 here. So if enable is made to 1 here, then only you can see the state is getting transition, the next state is getting transition from 0 to 1, and after that we are going to 7. Okay, so why I'm making this enable signal 0? Because here if again I've entered into idle state, so to stop the operation, not to enter into another write state or read state, if my enable is equal to 1, basically FSM operation will be disabled if my enable is equal to 0 from idle state to any other state. So that's the reason I'm making this enable equal to 0. And coming to this H address, initially this H address is equal to 0, and the transfer is starting from this cycle, this particular at 14, and at this particular cycle the transfer is starting. How I'm saying that transfer is starting at this cycle? Because if you can see, the present state is equal to 1, that is it is in the right state address. So in the right state address we are sending the first address, that is 000, that is a base address which the testbench user has given, and in the next cycle we are sending the data corresponding to this particular address. Okay, so the data is nothing but all 0001. Okay, and in the same cycle itself we are sending one more address which is corresponding to the next data address. This is corresponding to next data address. So in the next cycle we can see the address is changed, and also the data corresponding to the previous address was sent, and in the next cycle we are sending one more address which is corresponding to the next data. Okay, so in this cycle we can see the previous address data was sent, and this particular address data is sent here. So after sending all 4 beats of data, we are again entering into the state which is nothing but our idle state. So we are entering into our idle state after sending all these particular addresses. So this is how our master is sending, this is how our master is working with INCR4 burst. Yes. So that's all about this particular video. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. And if you are having any doubts or any questions, please feel free to comment in the comment section. Thank you for watching this video.